Okay, welcome back. So in this video, we're talking about sampling distributions, following up our discussion of normal distributions. Wanted to give you this slide so you can pause it if you'd like to, so you can come back to it if needed. A little bit of notation this video, but nothing too crazy. So if we're talking about sampling distributions, let's first start with what it means to sample something. To me, it makes me think of going to the grocery store on samples day. Like if you live in Fairbanks, go to Costco. Sometimes there are people out there giving samples of food. So it's a way to test what the broader population of that product tastes like, so you can know if you want to buy it, right? Or like cheese samplers, various samplers, like tasters if you're at like some kind of coffee shop or brewery or whatever it may be, right? So just giving literal examples of the broader population of cheese in this case. Or say you're painting a new room, you might get little samples of paint and paint little portions of the wall to have a more representative look of the broader population of paint that would inhabit those walls, so to speak, or cover those walls. And so in social science, we've talked about this before. Samples essentially groups that are meant to be representative of the broader population of interest. Um, and so this slide goes back to early in the course, so I won't go over it again. Um, but one example of inferential statistics are cases in which you might use a small sample to infer something about a broader population. I'm thinking of like when I was a college student, and I remember taking like math tests my first year. I was in a math class with some buddies on my dorm floor, and after the test, we would all come back to the dorm and be like, "Yo, what'd you think? Was that a little harder than usual? Like it felt harder than usual to me." And so by asking a few people how it went, it was kind of a way to try to gauge what the exam was like, right, and how you did. It was very imprecise, but nonetheless, it was something that at least made you feel better in the moment. Oftentimes, sometimes it made me feel worse. I wasn't the best student. Um, but anyway, so moving forward to sampling strategies. Sampling is something that is obviously extremely important in social science. It is, however, not the primary focus of this course, so I'm not going to get into the weeds here, so to speak. But I would like to at least introduce this content. And there are lots of ways we can define sampling, lots of things we should consider. But broadly speaking, let's just talk about two ways we can sample. One is without replacement, and one is with replacement. And so these are intuitive terms. So sampling without replacement means that each participant is not replaced before the next selection. And so, yeah, I'll show an example here. So this is the most common method in behavioral research. So this is what we tend to see. So for example, say we have 8 squares and we're selecting individual squares one at a time. And so if we have 8 of these and we want to know the probability of drawing a square marked A, then the first time we do this, the probability is 0.25, right? Assuming we haven't drawn anything else, at this point we have 2 A's, 8 total cards, so probability of 0.25, 25% chance. And then if we don't replace that A, and we make another draw, now the probability of selecting a square marked A has, you might guess, decreased. Now it's 1 out of 7, that 1A divided by the 7 total cards now. So now our probability is dropped to 0.14 or a 14% chance. Right, and so that's sampling without replacement. Sampling with replacement is just the opposite, right? So each time you make a selection, you replace participants before making the next selection. And so this ensures that the probability for selection is always the same across instances and across groups. However, this generally isn't necessary in social science research because populations are large. So for example, if we're studying a population of 100 women, probability of selecting the first woman is 1%. And then the probability of selecting the second woman is basically 1% still, right? The percentages won't drop for a while. The probabilities won't drop for a while. So generally speaking, with large enough populations, this really isn't an issue that we necessarily need to correct. But like I said, I wanted to broadly mention it, just give some context for the fact that social science research, we're technically doing not necessarily imprecise sampling, but when we're studying a large population, we have large samples, we generally don't need to worry about it. But if we were doing a small study, this might be something we should consider. Right, so that's just an example of the things to think about when developing sampling strategies. And like I said, it's extremely important, but it's not the main focus of this class. So um, again, we're skimming the surface here. In fact, I think, I only have a couple more slides related to sampling specifically before we get into sampling distributions. And so, like I said, good research always involves a good sample design. Um, and a sample design is essentially a specific plan or protocol for sampling, right? So what you're going to do. And this generally sample design must answer at least two questions. First is, does the order of selecting participants matter? We need to think about the order in which we select them. And following up our previous remarks, do we do it with or without replacement? And so those two questions can kind of lead to two broad strategies for sampling, or broad strategies for our purposes here. So theoretical and experimental or practical might be a more practical way to think of it. And so theoretical sampling, the importance of mentioning it here for your own learning and your own work is basically just to know that theoretical sampling is a basis for statistical theory. And so, in other words, statistics often have been developed with some assumptions about sampling. First is that the order of selecting individuals matters, and second is that we are sampling with replacement. And so there's some math here that I'm not going to go into, but you're welcome to pause if you want to spend a little bit more time on this. Practical sampling, practical meaning that it's what we typically tend to do. This is most common in behavioral research, and order generally does not matter, and each individual is not replaced before sampling again. So yeah, more math if you want to look at it. But again, just worth mentioning and providing context for how we draw samples and recognizing that in statistics and in social science research, what is ideal often is not what is realistic. And so we inherently have to sometimes accept a little bit of limitation in our ability to reach the theoretical goals we try to attain with our rigor and with our methods. And so you might say, okay, what's the point? Why are we talking about this? Well, first off, I guess not really first off, but generally speaking, it's because sampling matters, like I said, and because it will affect the accuracy of the parameters of our sample and how we interpret them. So for example, our sample mean or sample standard deviation. And fortunately, as you'll learn in this video, if we do good sampling, we don't have issues on that end, then we can trust that our parameters reflect population parameters. Or on average, our parameters, like the sample mean, the sample standard deviation, will reflect the population parameters, like the sample population, the sample variance. And the reason for this is that mean and variance are what we call unbiased estimators. So we'll walk through why that's the case and what we mean by that. And so in other words, basically what I'm saying here is that if we do good sampling, we can generally have a fair amount of confidence that our sample is actually representative of the broader population from a statistical standpoint. And so something we use to consider this, and something that will, I guess I was going to say, like, we'll use it to interpret statistics. And really, that is true, but really, when you're interpreting the statistics, like if you're conducting some descriptive statistics or frequencies or something like that, sometimes you might get a specific statistic called the standard error of the mean. That's something we'll talk about later. But basically, sampling distributions are a distribution that informs some of the statistics you'll see when you conduct your analyses, right? So even if you're not actively thinking about these, they are involved in the math that's happening behind the scenes, especially for using a program like Jamovi, where you're not actually handwriting the math yourself, right? So this is important to know because it's important, or it's an important part of the background process of doing statistical analyses. And so with sampling distribution, is a distribution of all the possible sample means that could be obtained in samples of a given size from the same population. Sample means or variances. That's a wordy definition, and honestly, the definitions in this unit or this particular video, I think, tend to get confusing because we're using the word sample and distribution lots of times in the same place. So to give you a graphic to hopefully help with that, so here we have, I hope you can see my mouse. Here we have the population up top, and you can imagine all these individual distributions down here are individual samples, right? So we're sampling from this population, and then each of these samples has their own unique sample mean. Then here, this is the distribution of sample means, or in other words, this is the sampling distribution. And so, in other words, yeah, and this is something we'll sort of prove as we go through this. But you can see here the sampling distribution, some characteristics are that it is, the standard deviation, the variance is smaller than that of the population, but the mean of the sampling distribution is the population mean, right? It is the same as the mean of the population, right? And so, yeah, well, like I said, we'll kind of talk about this in several different ways, and I'll provide some resources in Canvas for you to think about this and visualize and simulate it yourself. And so the benefit here is that by developing a sampling distribution, we can then compare our sample statistics to the mean and variance of the hypothetical population. Or in other words, again, these are things that help us to trust that our sample actually is representative of the population. Or in other words, is our sample mean a good estimator of the population mean? And I feel like this slide's a little confusingly worded. So if this trips you up, honestly, don't focus on this. Focus on the rest of the content because I will be more eloquent in other slides. But broadly speaking, like I said, the mean is an unbiased estimator, which is what enables us to have trust in the fact that the sampling distribution mean is going to be reflective of the population mean. In other words, means of any given sample are generally in aggregate going to trend towards the population mean. And that's because the mean is an unbiased estimator. What does that mean? Let me show you. Okay, this is, yeah, this is the same definition I just showed you, but I did want to mention a few resources here because especially at this point, basically this figure or image, there are two websites I'll provide where you can essentially simulate that and play with it yourself. And I'll record a video for Canvas of myself using it to show you. So this is one example here and a little screenshot of what it looks like. So this population is pulling or drawing these samples to create the sampling distribution. Another example here of a website. This one's, I think the user interface is a little less exciting, but this does give some details that the other one doesn't. So here you can see this is late in a simulation that I was running. You can see all the sampled values over what, like 12,000 sampled, or 12,000 participants, you could say. And you can see across those the sampling distribution of the sample means trended towards that of the population mean, right? So in other words, all the sample means, and this, I'm sorry, I'm explaining this poorly. I think I was doing samples of like 100, and I had it do it like a bunch of times. And so it kept adding more and more and more participants here. And all the individual samples that went into building this whole population here, all those means of those samples trended towards the population mean. And so again, if that's not making sense, I'll explain it better here in a sec. And I encourage you to go back to these websites to play around with it and hopefully solidify your understanding of the of what we mean when we say the mean is an unbiased estimator. So to depict this with an example, so suppose we have a population of 3 scores, 2, 5, and 8, and we want to select samples of size 2. So we're just doing it very simple here. So in other words, we have, if we calculate an overall mean here, 2, 5, and 8, overall mean is 5, overall sample mean rather. And now we want to select samples of size 2, or n equals 2, from a population of size 3. And so by doing this, we'll have 9 theoretical samples we could have, right? And so they're all listed out here. And this is a quick run. I'm about to explain this in much better detail. So we know now that our population mean is 5, right, based off of all the theoretical samples we could develop. And our sample mean was 5 as well. And so on average, what I'm saying here is that our sample mean is going to equal the population mean. And that premise, that our sample mean will generally equal the population mean, is known as the Central Limit Theorem. And so to, again, graphically depict what we just said, so we have a population and we have scores of 2, 5, and 8. And we want to select samples of size 2 from this population. This is what our sampling distribution is going to look like. If that doesn't totally make sense, I'm about to show you what I think is a cool graphic to depict all this. And so, in other words, what we're saying is that, this is our way of saying that the sample mean will, on average, equal the population mean. Okay, so to go into more detail there, so just like highlighting what we just talked about. So we're saying that we have this population, and the scores can either be 2, or 5, or 8. I apologize; these are meant to be gender neutral, not men. I am limited by icons in Microsoft PowerPoint. We have scores of 2, 5, or 8. Those are our possible scores. And so let's just go through all the theoretical samples we can get. So we could have 2 participants of scores of 2. In that case, their sample mean would be 2, right? Because 2 plus 2 over 2 is 2. Lots of 2's here. We could have a sample that's 2 and 5. Sample mean there would be 3.5. If we select them in order, right, if order matters here, in this theoretical sample, 5 plus 2, it's going to be 3.5 again. We could do the same thing with values that will lead us to sample means of 5. We'll have 2 sample means with values of 6.5, and then 1 sample mean with value of 8. These are all the possible combinations you can get in this theoretical sampling distribution where order matters and participants are replaced. I guess I should have clarified that. This is sampling with replacement, right? And so, in other words, you can select an individual with a score of 2, and then they will be replaced. You can select another individual with a score of 2, right? This is a theoretical piece here. And so if we remove the math column, then we just see the frequency of these sample means. We see that, okay, we have 1 sample mean of 2, we have 2 sample means of 3.5, 3 of 5, so on and so forth. And so that is the central limit theorem. That is how we go from this to this, right? This, the population distribution in which we are sampling with replacement and order matters, to the sampling distribution of the sample means, right? And so the visualizations you can play with in Canvas, or that I'll link to from Canvas, those are just other ways to depict this, right? So all these things are getting at the central limit theorem, stating that regardless of the distribution of scores in a population, the sampling distribution of sample means selected from that population will be approximately normally distributed. And so empirically then, thinking what we know about normal distributions, that means that at least 95% of possible sample means that you could select will fall within 2 standard deviations of the population mean, right? And so that's what we mean when we say that on average we can trust that our sample means are going to trend towards the population mean, right? Sometimes shit happens and we might get a sample that just really is not representative of our population. And that could mean that we did something wrong with our sampling, or it could just mean that it was a very rare case in which our sample did not fall within those 2 standard deviations, or even within 1 standard deviation, right? And so that's why any one study alone could be flawed. And so meta-analyses and comparisons across multiple studies are necessary in science, but nonetheless going to show that each individual study is still a contribution and that it's developing this broader, I guess you could say, a broader pool of samples with which we can extrapolate information and infer things about the broader population. And so that's a little bit about the mean. The variance is also an unbiased estimator. So in other words, we can use a sampling distribution to characterize sample variance. And so basically using the exact same example we just went through, plugging in this formula, basically what we're saying here is that the sample variance on average will trend towards the, or equal the population variance. So in other words, if our sample mean on average equals the population mean, then the same is true for our variance. Our sample variance on average will equal the population variance. However, this is not a normal distribution. So the sampling distribution of sample variances, this tends towards a positively skewed distribution, regardless of what the population distribution looks like. This is just a characteristic of variance. A reminder, positive skew means some scores fall substantially above other scores. So in other words, some samples can have much higher variances than others, but most will not, right? Most will be on this side of the distribution, right? That's where the mode is, right? Most frequent. Okay, and so I just wanted to mention the variance. Now let's go back to the sampling distribution of sample means, right? So here we were talking about the sampling distribution of sample variances. Now I want to be clear that this is different. Now we're going back to the sampling distribution of sample means, right? Central limit theorem stuff. And the variance of this down here, the sampling distribution of sample means, that variance is minimal. And yeah, as you can see, like the variance is smaller than that of the population just by the spread or dispersion of the data. And so we talked about sampling and its importance. Sampling error is the extent to which sample means selected from the population differ from one another, right? And so you can see here that samples do differ, right? That's just, again, a natural artifact of doing this kind of research and collecting samples with things that inherently vary. And so we refer to those differences as sampling error. And the overall goal in research is to try to minimize or reduce sampling error as much as possible. In other words, we're trying to get samples that are most representative of the population and the population parameters and statistics, but nonetheless error does occur. And so one new statistic related to this is called standard error, or standard error of the mean, right? And so this is essentially a way to infer something about the sampling error, or I guess maybe you could say the population error. Let me just explain it. Let me stick to my script here on the slides. So the standard error is the standard deviation of the sampling distribution of sample means. This is what I meant when I said that this one gets confusing. It might be worth watching this one multiple times, honestly. So in other words, the standard error is the standard deviation of this, right? This is the sampling distribution of sample means. This has a standard deviation, right? We can quantify that. And the standard deviation of this is known as standard error, right? So in other words, if we have a really large standard error, it means that there's a wide variance here, which means that we just have a less representative sampling distribution of the population. Or in other words, the samples we're collecting are varying a lot more than they otherwise could, right, than if we had a sampling distribution with a small standard error. That means that the samples we're collecting from the population are generally more tightly knit, right? They're more representative of the population's mean, right? So um, that's essentially what we mean when we say standard error of the mean. And we need this if we're going to draw the sampling distribution, right? Like in this case, we have a mean, but we don't have a standard error or standard deviation written out here. So we'll need that if we want to actually draw the distribution accurately. And so a pop quiz for you from a previous module. Standard deviation is the square root of what? Positive, you need more time. The answer is variance. Right, and so this the equation or formula for standard error looks like that of standard deviation, right? We're taking a square root of variance, right? Except in this case, it's the variance of a sampling distribution of sample means. Confusing, I know. Like I said, just give it some time, you'll get there. And this here is the symbol for standard error. So standard error of the mean equals the square root of the variance of a sampling distribution of sample means, where that, the variance of a sampling distribution of sample means, equals this. Sample mean minus population mean squared divided by n sub n, right? Population n sub sample size. Yeah, so lots to do here, or lots to think about. But simply too, if we know the population variance, then and we have our sample size, then we can use that to calculate the standard error of the mean. Yeah, so these equations, if you need them, or when you need them, I suppose. Quick note that there are two broad factors that decrease standard error. As the population standard deviation decreases, standard error decreases. And decreased standard error is good, right? That means that we're having less sampling error. Our samples are varying less and less. Or they're differing less and less, rather. And so, yeah, so in other words, as the population standard deviation decreases, as the population becomes a little bit more compact or tight, I suppose you could say, standard error also is becoming more compact, less dispersed. And then as sample size increases, standard error decreases. So in other words, if we're collecting from a population with a smaller standard deviation, or if we're collecting from a larger sample size, then we're going to have reduced standard error, which is good. And so to give an example of drawing out a sampling distribution, so say we have a random sample of 100 college students, and they're asked to state the number of hours they spend studying during finals week. So the mean is 20 hours per week, and the standard deviation is 15 hours per week, and we want to construct the sampling distribution. Three broad steps to do this. First, identify the mean of the sampling distribution. Second is to compute the standard error. And third is to draw the distribution, right? Distribute the possible sample means, 3 standard errors above and below the mean. In other words, just draw it out like would any other distribution with the mean and the standard deviations. Except in this case, the standard deviations represent the standard error. So for step 1, what's the mean? Well, we have it is 20. That's mu. Sigma is 15. Might as well write that out. And our random sample is an n of 100. Second, compute the standard error of the mean. That's going to be easy. Let's use the easy formula, right? Because we know our standard deviation, population standard deviation. We know our sample size. We can reduce this formula. And then we get 15 divided by square root of 100 equals 1.5. There you have it. We have our standard error. Oh, whoops. Oh my goodness, I'm sorry. Third is to just draw it out, right? And so when we do that, we'll draw a distribution with a population mean of 20 and standard errors or standard deviations of 1.5. And so this is what that looks like. Whoops, my animations are messed up here. Wow, that was pretty bad. I apologize. And there you have it, right? We have our distribution, our sampling distribution of sample means, population mean of 20, and then we see our standard error of 1.5 plus or minus. So that means that 60, or what was it, 66, no, 68% of samples that we could collect would be between, would have, okay, let me rephrase. 68% of samples we collect from this population would have sample means that range between 18.5 and 21.5. Right, that's a basic interpretation of the sampling distribution of sample means once we know our standard error and presumably have the population mean too. So I hope this was informative. Like I said, if this doesn't stick, that's okay. Give it some time, and then give it another watch, and then just let us know if you have any questions. We'll see you next time.